Hello, I'm Daniela Vasquez, and today with my team, we're going to be talking about our ideal glassware design for our class. We will be starting with the introduction. During this project, we show how we started our investigation sending a survey to all of the people we know, making them answer a series of questions that will help us determine what type of design is the one that people desire at the moment. Based on that, we made a model design and started choosing our functions representing the figure we wanted for our glass. Then we visualized the 3D graph and provided the corresponding code. Now we will be talking about our problem description. The glass industry faces an increasing competition and a demand for innovative, aesthetically pleasing products, requiring the application of mathematical modeling and technology to design drinking glasses that meet consumer preferences. We hope to accomplish with this project is to incorporate computational simulations and data-driven approaches that can shape the industry and optimize glass thickness, shape, and weight distribution to enhance both functionality and user satisfaction while reducing material waste and production costs. Our main objectives is to build a design on a programming language, design that said glass, and ensure that the design is not only visually appealing but also ergonomic, durable, and practical for manufacturing.
So, what our market analysis told us was that over 50% of the participants preferred a classical style for the glass, and they liked the commodity more than the appearance of the glass of water. Now, the reason we chose the glass to be for water is because most of our participants were over 51 years of age, and they, as you can see here, they preferred to drink water. Now, the intersections of the answers of the survey was that they all preferred the design to be classical for water, that it had a little bit of innovation, and that it was glass. Now, also, if we want to value to grade the commodity versus design versus innovation, most of them, the three of them coincided in the fact that they wanted innovation, commodity, and classical designs, but they wanted innovation more than anything else. So last thing here is the size, and here they wanted they all preferred the glass of water to be be for a volume of between 350 to 500 milliliters. Now what we got from this data is that we can say that innovation is a key driving factor in consumer preferences. However, the thing is that they did want innovation, but they wanted to keep style. So we had to suit them in both of those areas. So they want something to be comfortable to drink, but also have the capacity enough to hold the water they want to drink, and have innovative qualities.
Later, we decided to separate the modulation by two parts, allowing us to make a precise modulation by its geometry. So, the first parameter is the inner modulation. The inner surface of the glass is described by the curvature and contour of the inner part, ensuring a smooth transition between different sections. And the second parameter is the outer equation. It's similar at the inner one, but the equations are slightly different from those of the inner surface to account for the thickness of the glass. By modulating both the inner and the outer surface separately, the structural integrity and physical properties of the glass can be analyzed accurately. Now, in this slide, we're showing the equations that we use to modulate the glass separated by each parameter after adjusting them. For the first parameter, the inner glass equations and the outer glass equations have a slightly change in the last part of the equation. Like I said before, this show us the thickness of the glass. And for every first, every second, and every third equation in each parameter, we have the ranges. We have, for the first equations of each inner and outer parameter, we have 0 minus equal x minus equal 0.31. That this show us the base of the glass. For the second one, we have 0.3 minus equal x minus equal 2.2. That this show us the principal base of the glass, the part that has the hand grip. And for the third equation, we have 2.2 minus equal x minus equal 8. That this show us the rest part of the body of the glass.
In order to create our 3D code, we use rotational surfaces and symmetry in Python. This requires numerical methods and computational libraries like NumPy and Matplotlib to generate a more smooth, rationally symmetrical shape. The process starts with, as we have mentioned, defining a 2D profile of the corpse's outer contour and calculating its thickness to establish the inner surface. We then apply rotational symmetry, revolving the profile around a central vertical axis to create the 3D shape. As you can see here, this is the 3D shape, and we use these rotational matrices algorithms to update the coordinates in the 3D space. So as you can see here, the three main matrices are the rotation around the x-axis, the rotation around the y-axis, and the rotation around the z-axis. The rotation around the x-axis adjusts height and depth, while the y-axis changes the height and depth. And the z-axis rotates the shape in a circular motion, as you can see here. Each matrix applies sine and cosine functions to transform points more accurately. By rotating the 2D profile at multiple angles, we generate a complete surface of revolution that forms the cup. This shows a little bit of our code that we use to properly plot and graph the 3D model. As you can see, NumPy effectively allows us to compute these transformations, while Matplotlib helps us visualize both the 2D outlines and the final 3D model. This approach using Python also allows us to assure accuracy and a more smooth design for our cup, using both mathematical principles with the NumPy libraries and programming with Python.
Today I'll explain how we calculated the volume of glass using piecewise functions and numerical integration. We know that the glass has an outer profile, meaning the shape of the glass itself, and an inner profile, which is the space where the liquid goes. The class is defined by piecewise functions for both the outer and the inner profiles. These functions were demonstrated in the previous slides. These functions are then combined to create continuous curves for the glass. For the calculation of the volume, we use the disk method, which I have shown the formula right in the slide. And this formula involves revolving these profiles around the x-axis. We calculate the outer volume by integrating the square of the outer profile over its interval, and the inner value by integrating the square of the inner profile over its interval. To calculate the volume of the material, first we have to add the integrals of the outer part of the glass, and that will give us the total volume of the outer part. And we do the same thing for the inner volume. And to get the complete volume of the material, we subtract the outer volume minus the inner volume. And that gives us the result. Now for the liquid capacity is the same as the inner volume. Now for the numerical integration, we use the trapezoidal rule to integrate the volumes. The trapezoidal rule approximates the area under the curve by dividing it into small trapezoids, making it efficient for this calculation. As for the results, the code will show the value of the material as 22.23 cubic inches, and the liquid capacity of 113.74 ounces. And that's it. Thank you.
Now I will be talking about cost optimization. We divided this in 4 different groups. But before we get to that, I want to talk to you about the cost optimization. In order to justify the final cost per unit of the glass, it is necessary to break down costs that add up to such total. So these are how the 4 different distributed themes that we have. First, we have the raw material costs. We ended up having 3 raw materials, which are silica sand, which comes at 5,000 to 20,000 per ton Mexican pesos. Then we have sodium carbonate at 3,000 to 15,000 Mexican pesos, again per ton. We have limestone from 2,000 to 10,000 Mexican pesos per ton. Approximately, that is 0.02 to 0.03 Mexican pesos per glass. Then we're going to go on to the next part, which is the labor costs. And depending on the production cell, also assuming the same production of 16,000 glasses per month, the labor will cost about 0.94 to 3.75 Mexican pesos. And then we have our indirect manufacturing costs, which are, we are contemplating on a scenery that counts maintenance, insurance, rent, etc. And this will be approximately 16,210 Mexican pesos. And for 6,000 glasses, that would be approximately 1 Mexican peso per glass. Then we have finally our economy cell in an efficient industrial production. The estimation was made on a general production of calculations, specially filtering from Mexico, including CFA energy rates and average industry wages. We assumed economy cell in an efficient industrial production process. These quantities are estimates and may vary depending on factors specific to each production plant as a manufacturing, such as operational efficiency, production cell, and geographic location of the industry. This project encouraged creativity, critical thinking, and a deeper appreciation for the intersection of design, engineering, and consumer driven innovation. The ability to create, iterate, and refine our model using 3D visualization. In conclusion, this process highlights the power of computational tools in revolutionizing our traditional industries, paving the way for more personalized, sustainable, and functional designs in the future. Thank you.